In this video, we're going to be combining our knowledge of the relationships between pressure, volume, temperature, and the number of moles that we learned in the previous two videos in order to derive something that we call the ideal gas law. Now, if we examine the relationships we've learned, we know that pressure and volume have an inverse relationship to each other because as we increase the amount of pressure that a gas is subjected to, that pushes gas particles closer together so that they occupy a lower volume. We know that temperature has a direct relationship with both pressure and volume because as we increase temperature, gas particles move faster and therefore they exert more force on the sides of the container, meaning that an increase in temperature causes an increase in pressure. And if we were to increase temperature because gas molecules move faster, they would move farther away from each other and occupy a greater volume. We also know that the number of moles of a gas has a direct relationship with the volume, assuming that pressure and temperature are kept constant. Increasing the number of moles of a gas means that that gas is going to occupy a greater volume. Now, just like with the other gas laws, how we used K as a proportionality constant, in this case, our proportionality constant is going to be represented by the letter R. And the units for R match the units that we have in this relationship here. So the units for pressure that we know of are kilopascals, the unit for volume is liters, the unit for temperature is degrees Kelvin, and the unit for moles is, well, moles. Now, through experimentation, chemists actually determined that assuming that we're working with all of these variables here, the value for R on Earth is approximately 8.314. Now, what this allows us to do is actually to use this relationship in order to do calculations to calculate pressure, volume, temperature, or the number of moles of any gas as long as it follows the ideal gas conditions. We can use R and rewrite this formula slightly, so if I just write out PV is equal to NT is equal to R, and let's keep in the units just to see that this all balances out. Now, what we're going to do is we're going to modify this expression by moving N and T over to this side by multiplying both sides by N and by T. Now, if we do that, that would mean because the unit for T is degrees Kelvin appears in both the numerator and the denominator, so it cancels, and likewise with moles, and that allows us to come up with an expression that has no fractions and shows the relationship between all four variables with our proportionality constant. PV is equal to nRT, and this is the ideal gas law that can be used to calculate any of these variables for any ideal gas as long as we have all of the other information. And we can use this formula in order to show where a number that we used that required further explanation in the stoichiometry unit comes from. If we remember what the conditions for standard temperature and pressure are, at standard temperature and pressure, our temperature is equal to 0 degrees Celsius, which we know is 273 degrees Kelvin, and our atmospheric pressure is 1 atmosphere, which is 101.3 kilopascals. Now, if we put all of this information into PV equals nRT, we can use this to find out what the volume of 1 mole of an ideal gas is at this conditions. So let's modify PV equals nRT so that volume is isolated, and we can do this by dividing both sides by pressure. So volume is equal to the number of moles times R times the temperature in degrees Kelvin divided by the gas pressure. And if we insert our numbers here for the conditions, we know that we're dealing with 1 mole of gas. We know that the proportionality constant is 8.314 kilopascals times liters divided by number of moles times degrees Kelvin. And we multiply our temperature by that which is 273 degrees Kelvin, and then we divide by the pressure at STP, which is 101.3 kilopascals. And if we check the unit, we see that moles appears in the numerator and denominator, so it cancels. So does kilopascals, and so does degrees Kelvin, meaning that we have successfully isolated liters. And if you put this into your calculator, you get that this number comes to approximately 22.4 liters. This is where our assumption of knowing that 1 mole of any gas occupies 22.4 liters at standard temperature and pressure, this is where that ratio comes from. Now in the next video, we're going to look at how to use PV is equal to nRT in order to solve for pressure, volume, number of moles, and temperature at non-STP conditions, and therefore how we can use this in order to do stoichiometry problems at non-STP conditions.